Hello, today we will be deriving the Euler-Lagrange equation. The Euler-Lagrange equation is an equation that you can use, differential equation you can use to derive the equation of motion of a system. It's another approach to take besides just your classical Newtonian mechanics. In order to understand the derivation, there's some concepts that we should first be comfortable with, and so it's the concept of basically finding stationary points. So in one single variable calculus, a stationary point would be a point where the slope is 0. So it's important I'm showing 2 points for a reason, because the stationary point does not necessarily mean it's the point where you have your greatest value or your point where you have the smallest value. As you can see here, both these points are stationary points. The slope here is 0, right? This x, and the slope here is also 0. So we call these stationary points. Another concept to become familiar with or comfortable with is the idea that if you were at that stationary point and went a very small amount to the left or the right, you wouldn't have any change. So it's not terribly difficult to understand that. For example, if I'm here at point 1, I'm gonna say 1 there to indicate that I'm at this exact point. And if I went, if we're saying that equals 0, and then if I'm still at that point, and if I just went infinitesimal, a key word is infinitesimal, very, limit some small difference, and that difference as the difference decreases, it approaches 0, not at 0, but approaches 0. So we'll call that delta x. So here we said that's 0, right? So if you have that infinitesimal amount, or if you move it, I should say, by a small amount, that would still be equal to 0. This is sort of like saying you're moving it, but still at that point, if that makes sense, a very small amount. So if you're still at that point, I think this is very important to understand actually. So if you're still at that point, and if you move it an infinitesimal amount, that change, actually I should say that it's equal to 0, but that's also equal to df. So df, that change in df, right, and that value doesn't change, it's 0. So that's a key point, I think, to understand. So see, there's the idea of a functional. It's also important to understand what that is. Say we have in 3D space some plane, and on this plane we have 2 points, point there, point there. Now the question is asked, what path do you have to take to get from point 1 to point 2? That would be the smallest path, or where the length is the smallest, right? So there's many paths you could take. You could take some really crazy path, but there's only one path that would give you the smallest, or that would be the shortest distance. And if you think of that, the smallest, that word smallest, or stationary, to be like a stationary point, right? So if we were to take absolutely every single path you could think of, and somehow, I guess, have some quantity to represent something about that path, and then you compare that quantity to other potential paths, some small difference between this path here. Well, let's say we know what this path is that would give us the shortest distance, and say if we know what that path is, and then if you deviate just an infinitesimal amount from that path, then that change in the path length would be 0. That's analogous to saying, df dx if single variable calculus times delta x equals df equals 0, right? So at this point, if at that point you're at if the slope is 0 at this point, then a very small change from that point wouldn't change that function, so you would have 0. So the same idea can be used here. So if you have a path which is the shortest path, the small change from that path would cause a change in the quantity. We haven't defined what that quantity is yet. That change in quantity would be 0. So now let's define what quantity we're talking about. The quantity that we're talking about is called the action. So now let's define what the action is. So this action is this thing that we're saying if we know the action of this path, and this path happens to be the shortest path, then if you were to change the path by some small amount, the action could change, right? But if that path is the shortest path, you can, if you have found the shortest path, then that action, the change in action would be 0. So, because of course the analogy to that is one variable, a single variable calculus that we just drew. So now let's define what that action is. So the action is defined as some integral of, we'll call it L. L is the path, dt. So I should say at time 1 and at time 2. So this is this L is it's very general right now. We're talking in a general sense. This L then is some function of something, and the action then is a function of functions. This will output some number. But now, if you change this L, that number will change. That's just a scalar, right? Because this is from T1 to T2. So now let's go ahead and label this axis. Let's say that L is a function of some quantity q and its time derivative q dot. Now, good question to ask is how do we, this is very, like I said, general, but how did you find, what would q and q dot be? Some very smart people discovered a relationship, I guess, between this idea of taking the action and finding the stationary point of that action, and then what function, I guess, are you using to get your action, or what is that the space of functions, I should say, that you can use to get your action, and the space of functions that you can use are dependent on some quantity q and its time derivative q dot. So if we call this L, then we say that's q, we say that's q dot. can, just to be clear, q and q dot, this means that L is a function of q and q dot, and if you take the action of this very small, this stationary, call a stationary function, I guess, because if you change this function by a very small amount, if you change the length of this by a small amount, the change should be 0. But this by itself, when you figure out the integral of this, will give you some number. But now, once again, if we say that we change this action by a small amount, this will be equal to 0 if this is, like we said, if this is the shortest path. So let's see, so how do we figure out how to take the very small change in action and represent it here? Let's see. So first, let's think about it a bit. If we have, how do we change it, I guess? How do we represent a change, a very small change? So if we had q, if we had some, q that axis and time on that axis, and say we know that, q has, this is a function of q, so q is a function of t. This is how it changes. And of course, we're saying that this L, this function L is dependent on q, and q dot, haven't drawn q dot yet, but now we say that, okay, how do we evaluate this? What do we do here to see if we make some small change in L? Which, how do you make a small change in L? Well, maybe you make a small change in q and q dot, right? So to make a small change in q, let's add to this function, which we say now is going to be the q, which produces, is associated q and q dot, which when you plug in those sets of numbers into this L, right, this function L, and this function L will give you your action, which we're saying is going to be some number, but it's going to be the smallest or number, or it's going to be at a stationary point, right? And so once again, a stationary point is where you change it just a little bit. It doesn't change to 0, so that's what we have there. But now if you add to this some function, let's call it v. I'm drawing this way for a reason. This function v could be any function that you add to q, but one thing that we can't change, so well, first if we add, let's see, I'll call this vt. If we add vt to q, what's that going to look like? Well, it's going to change it, just a bit, right? So that's the new path. And like I said, this v could be any function with the following constraint. Well, the constraint is that v at this time 1 and v at this time 2 has to be 0. Why? Because we know that these 2 points, these are boundary conditions, so this can't change. Whatever happens in between those boundary conditions, that's allowed, but we know that these 2 points can't change. So if we already said, there's a q and a q dot here, and a q and q dot here that gives us this value, then you essentially have to guarantee that those 2 values don't change. So the function v at t1 has to equal 0. The function v at t2 also has to equal 0. Why? Because let's say this is a, value a, and this is some value b. So this value a at t1 has to can't change, and this value b at t2 can't change. So that's why the function v at t1 has to be 0, function v at t2 has to be 0. So q1 q at t1 equals a. Here, let's write it over here, just so we make sure we understand the concept. So we're saying q at t1 has to equal a, and q at t2 has to equal b. So if we add then to t1, right, we add that v at t1. If it still has to be a, then this has to be 0, right? And basically simple algebra, right? So we already defined what q1 at q at t1 has to be equal to. So I mean, we can really drive the point home. Subtract a from both sides equals 0. And of course, this is true for q at t2 as well. So it's very important to keep in mind. And the same is true for the time derivative. So we'll end up using this idea. So I will say then up here, so v at, once again, v, what is v? V is this second function that we're adding to q, which we're using to evaluate what happens to the action. We're using to evaluate, see what happens to the action, because we're saying that if we have chosen the stationary function, then any small change to that stationary function that correlates to some small change in the action, and that small change in action is 0 if we've chosen the correct stationary function. So t1 equals 0, v at t2 equals 0, and the same is true for the velocity as well. So there's a velocity q dot. That's what I'm sorry. I just said that time derivative of q is q dot, and well, that's some hint of a little power of where we're headed, I guess, is q dot. So oftentimes the velocity of the system, right? Which I think so anytime you have dealing with particles, q dot will be the velocity, right? So let's see, so v dot at time t1 equals 0, and v dot at t2 equals 0. I'm trying to be very careful with what I say. I'm not by no means expert in the subject. Just think I've understand it to the point where I'm able to communicate it, and hopefully help you get viewers to also have better insight into how it works. But still, if I make a mistake, please let me know in the comments. I think I've understood to the point where I can show some examples and go through the procedure, the derivation. But like I said, I'm not an expert in the subject. Okay, so let's see. So this is very important. I'm gonna make some room now. And the same is done for q dot here. So I drew it graphically what v is doing, and then this basically the same thing can be said of q dot and adding v dot, right? Okay. Okay, so let's see. So now, so we took this action. We'll call this action 1. So this is the action 1. This is some number, and this number is you get from integrating this function, which we said is the stationary function. Now, this then, the change in the action, very small change in the action, we'll say will be, I'll call it A2. A2 is going to be the very small change in the action caused by the very small changes in Q and Q dot, which in turn causes a very small change in this line here, this path. That's what Q2 is. So A2, that's what A2 is. A2 minus A1 is equal to 0. So, right, so we start at A1. This is the value we get from this function, from integrating this function. And we change it, so A2 is a very small change. Could be any small change to this function, and that small change should be equal 0 if we've chosen this as our stationary function. Okay, so we have A1 there. Now how do we get A2? Well, let's see. A2, okay, so let's look at an analogy again in single variable calculus. If we have some some function here, and if we want to see what happens to, here, this is actually, could be represented this way. This is better. So we start here at some, call it F1. The analogy here is, A1. And we want to go to some F2. I draw it as a large change, but in reality it's a very small change. So F2 is represented here as A2, right? Or the idea, I guess. And this F2 is caused by some very small change in x. That's dx. So let's see, if we start at F1, and if we went to F2 by some small change dx, how do we get the value of F2? Well, we know that F2 is simply, this is first order approximation, meaning if you take the Taylor series of this, you'll have some higher order terms, but when dealing with first order approximation, you can say that F2 would be, starting, F2 would be the df over dx, the slope, right, at that point 1 times the change, right, dx plus where it started from F1, right? So let's see, it's not too bad. And then, right, okay, so A2, let's get A2. So let's see, well, let's, A2. Well, first, let's remember how we're changing L. We're changing L by adding some small amount to this Q, and some small amount to this Q dot. So let's represent A2 that way first. So it's still the same limits, boundary conditions, T1 and T2, but now it's Q, and to this Q we add V, right? And then right now it's just notation, right? Q dot, and to this Q dot we add V dot, right? And then dt. Okay. So now what do we do? Let's see. A2. So that is A2, right? Yes. So we have a new value L by just, actually we didn't use this yet, did we? No. Not sure if we will use it. Let's see. Okay, so we have a very small change in Q caused by V, a small change in Q dot caused by V dot, right? Now let's, Oh, so what is this equal to? That's right. So you can represent this. Oh, we will use it. Yes, same concept we will use. We will represent this then by, using this idea here. I'm going to erase this. Okay, so what does that mean then? Okay, so starting, starting, right? So A2, so starting at A1, or I'm sorry, starting at L, so let's evaluate this, right? So, well, first L is going to be, a change in where you started from, so a change in that, right? So change, the analogy is F1, so let's go ahead and say LQ, Q dot, and then add it to this is going to be the slope multiplied by the small change, right? Okay, so the slope then, here, the slope at this point, right? Here's the analogy, right? It's going to be, and this is where the partial derivatives come into play. You have a function that's depending on two quantities. So the slope, you look at the partial of L with respect to, Q times that small change, right? Just like we did here, this slope times that small change. But now in this case, we define that small change as V, right? And then add it to this. We will add on the other partial derivative. So the partial derivative L with respect to Q dot. Now how do we change Q? Very small change in Q was caused by V dot. Okay? So we're saying, what are we saying now? We're saying that this is this. These two things are equivalent. That's what we're saying. And the analogy here is, this is our F2 here. How do we get F2? Well, we have to get the, well, first we start off, I had it flipped, but we start at some value, F1. So F1 here would be represented by this, right? This is the starting value, and to figure out what F2 is, we add to that the product, or in this case products, of the slope at that point times that very small change. So slope at that point times the very small change. Again, for partial derivatives, you have to, it's a bit different, but here's where this comes into play. So the slope, dl, or partial of L with respect to Q times that very small change, right, plus the partial of L with respect to Q dot times that very small change. So I'm hoping you're comfortable with that. Let's see. If not, real quickly, we can take a look at what that actually means visually. Graphically, it's not obvious there, I hope, but I'm just going to say, just as a little detour, I guess, to really understand what's going on here, x and y. So if you have some function that's some function that's dependent on x and y, if I'm at this point, and if I want to figure out what the slope is at this point, this slope would be some I guess, the analog to slope in single variable calculus. We would call that the gradient. And the gradient would be the, so if we just looked at what happens if you move in this direction, that would be the partial of f. Yeah, say partial because this f is no longer dependent on just one variable, so it would be partial of f with respect to y, plus what happens if you just move in that direction, partial of f with respect to x. So this is called the gradient at any point on this surface. Now we know, knowing what that gradient is, right? We add or multiply that the terms of that gradient by the appropriate small increment, and the appropriate small increment in this case would be for this term v, because we're looking at changing q by a very small amount v, and then in this term here where you're looking at the partial of L with respect to q dot will be v dot, right? So hopefully you're comfortable with that. Some of this you may want to review, partial derivatives, and we'll also be getting into the integration by parts. Okay, so let's see. So that's good. So we figured out then what this is equivalent to. So this is equivalent to that. So I'll make some room. Okay, so let's see here. Certain things I want to keep. So I'm gonna just move some stuff and erase some stuff. So copy and erase some stuff. A2 minus A1 equals 0. If we defined A1, I'm going to erase this. Now I'm going to go ahead and basically take this and substitute it for that. Okay, so let's see. Okay, good. Oh, hold on, forgot the dt. Okay, I should also note we're only looking at a one-dimensional problem, right? So I guess I should maybe say what Q is. So Q is would be the position, right? If you're looking at a particle. So the position of a particle, one dimension. So maybe it starts here at time 1, has some velocity here. So Q is going to be the position, and Q dot is going to be the velocity. And then at this point, it's going to be Q2 and Q2 dot. But if you have this is one-dimensional. If you have 2 dimensions or 3 dimensions, basically you would do this for every dimension in order to get your equations of motion. So right now I'm just saying that this is just Q1 and this is Q1 dot. Well, actually I don't really have to say it's Q1 because there's no other Q's, but if there were other Q's, other dimensions with its associated velocities, you would do this same procedure for those other dimensions and corresponding velocities. So Q, x and x dot, y dot, z dot. Okay, so let's see. So now let's see what happens if we just do some substitution. So a lot of this is going to involve some substitution, just understanding conceptually of what's going on and being comfortable with it. So A2 is this. Another thing, I think it's important to realize that, I forget what the term is, distributive property, I think, where, the integration and taking the derivatives, it has a distributive property. That's where, it's a side note, like if I have A times B plus C, and that's equivalent to A, B plus AC. So I can basically take this integral and do it in distributive for each term, this term, this term, this term, along with the associated dt. So that's what I'll do now. And I'm doing that for a reason, to make it clear. So this now is A2, right? This is A2, right? A2, and now I'm subtracting A1. So this is A1, subtract A1. Okay, now we're saying that this is equal to 0, if this is truly the stationary function. Okay, so what can we do here? Looks like we have some terms that are equivalent, but with opposite sign, right? So see, this and this cancel. It's nice. Now we're left with these two. Okay, so once again, I will have to make some room. What should we erase? I'm going to erase this stuff up here. Should we keep that? Yeah, we can erase that too. Okay, so now I'm just going to move this up here, and we're going to do some manipulation. Okay, see, make sure you guys can see what's going on. Good. Okay, so equals. Well, now I'm going to go ahead and make use of that distributive property and for integration, just to make it cleaner. Oh, should I do that? Yeah, okay. Yeah, that saves some space here. Okay. Alright, good. Okay. Now, okay, so this is where we want to do some integration by parts. We have a v and we have a v dot. Now something interesting happens. What if we can get, well, we can, it's just some calculus. We can go ahead and get this term so that it's, we have v here. We have v here instead of v dot. How do we do that? some integration by parts. So if you recall, let's do it quick here. If I have u and v, well, I run out of room. Okay, I might run out of room. Well, we'll see what happens. Okay, so the derivative, time derivative of u times v is equal to u dot times v plus u times v dot. Okay, so let's see what happens if we integrate that. Okay, so if we integrate that, this then becomes, get rid of that, but now this is going to be at the limits t1 and t2, that equals the integral of u times v dt plus the, let me see, make sure I still have my limits, because I mean, this is a definite integral, not indefinite integral, meaning that we do know what we're, the points that we're integrating between. So t1 and t2. t1 and t2, u and v dot. Okay, so now let's just look here what we can do. So look, we have a partial of L with respect to Q. What if we called that U for this purposes? I don't know what we would call that. The word for the we're doing some basically some substitution, right? We're just looking at this form and looking at this and seeing, you know, all it is just, you know, calling something instead of A calling it B, just change in what you're calling the variables, right? So see, what if we called that U, right? So what if we said that U is equal to this? And then what if we said that, oh, look at that, so V dot, what if we said V dot is equal to V dot, right? So V dot is equal to V dot. Now what do we have here? And the situation that we're in is we have this right now, is here, right? Because U is the partial L with respect to Q. V dot is V dot, right? Well, I've got my dt, and then the integral there. So if we solved for this, solve for that, what do we get? Okay, so just moving that to that side, right? I'm running out of room, so I'll have to, I'm going to jump over here. I think it's important for us to see this step. So, so I'm going to solve for U and V dot. That equals U, the product of U and V evaluated at the limits T1 and T2 minus that. Minus that U dot V dt evaluated at T1 and T2. Okay, so there's something very interesting here. Alright, so what does it mean when you evaluate integral at its limits? So this is going to be U at T2 times V at T2 minus U at T1 times V at T1. Now I'll write it just so that we're clear. U at T2 times V at T2 minus U at T1 times V at T1. So what is this equal to? Well, I can tell you what this is equal to, because we know that V at T1 is equal to 0, and we know that V at T2 is equal to 0, right? So this is equal to 0, and that's equal to 0, anything times 0 is going to be 0, anything times 0 is going to be 0. So this term is equal to 0. So yeah, so that's pretty nice. If that's equal to 0, then it simplifies. I'm just going to erase it, because we know it's equal to 0. So now we know that this is equal to that, right? And once again, u is going to be the partial of L with respect to dq. So now let's go ahead and, just so that we're clear, I will put that in here. Partial, oh, no, not quite, yeah, 1 second. I'll make the substitution first. Okay. So okay. I'm gonna erase this. No, not yet. I have to erase something. So I'll erase this. Okay, and I'll erase. So let's just review where we're at. We're here now, right? So we're trying to get this into a form where we have just a v. We have a v here instead of a v dot. So let's see, u dot. So we know u is equal to that. So what is u dot? U dot would be the time derivative of that. Right, so let's go ahead and, what does that look like? Looks like this. Right? Times v, then dt. And what else will I erase? I have to erase some more stuff. I'm going to erase this too. Okay, so I'm going to still need that. Let's take, so where do we see this? We see this here, right? So this is there. So let's go ahead and make the substitution. Do you see what we're substituting now? We are going to substitute this for this. Hope you see that, right? So let's go ahead and do that. Okay. So I'm going to move this here and make the substitution. Right there, right? Yep. Okay, so now good. We have two terms, here and here. Now let's see. We have okay, so we have the v shows up in both terms. What is v again? V is the function that we added to the function q in order to evaluate what happens if we changed the function L, right, in order to change the action, right? And we said if we change the action by some small amount, it should be 0 if this is going to be the stationary function. Okay. So let's see. let's go ahead and just factor out this v. I'm not doing anything special here. I'm just taking out the v. Okay. And I'm just going to just change how the brackets look, just to kind of drive the point home that I'm trying to make. Okay, so we're saying, let's think about this, and this is where we have to kind of understand again, conceptually. Some of the stuff was, just calculus and going through the methodology of what's going on. Now, at this point, we have to kind of look at it and see what's conceptually understand, make some conclusions, logical conclusions. So if we're taking the integral of this, then we're saying that it always has to be 0, right? So, but we know that this v can be any function as long as its endpoints are 0, right? Other than that, there's no real constraint on what v can be. But we're saying that if you take the integral of this, it always has to be 0. How do you guarantee that that will always be 0? Well, you can guarantee, well, this always can't be 0, right? This, though, we can say will always be 0. And if that's the case, we can guarantee that the integral of this will always be 0. So let's take what's in brackets here and pull it out, and now we'll say what we're left with. Dun 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 is the Euler Lagrange equation. So dt. Oh, hold on. I missed somewhere. I missed a q dot somewhere, and I think I missed it here. Did I miss it there? Yes, I did. That should be q dot. I apologize. Somewhere along the way, I missed. I didn't bring that q dot along. Yep. Yep. Yeah, because that's v dot, and that has to be q dot, right? Luckily, I know that because I know what the form of the Euler Lagrange equation needs to be. So it's a careless mistake, but okay. Let's see, q dot. Yeah, there's a q dot here as well. Q dot here. A lot of dots. Okay, and I think we're good there. So somewhere along the way, I missed a dot. Hopefully, you guys can find it at the point at which I didn't add in the dot. But we're saying that this then equals 0, and that's it. That is the Euler Lagrange equation.